recommendation would you have? Tell me about it. Eating cars.
Yeah, you know what the craziest thing is? I was listening to NPR and they mentioned something about Latvia. Remember you were talking about?
Oh, Latvia. The country?
Yeah, Latvia. I was like, wow. That's right.
All right, the recording is on, so I'm going to get started. Are there any questions about the exam on Thursday? What exam? Nobody told me anything about an exam. Yeah, that exam. Any questions about the exam? It is open book, open notes. Okay, just want to make sure that everybody is ready for it. Yep. How many questions? I do not know yet. I will probably know tomorrow night. But the format of the questions will be very similar to the ones that you have seen before, in the practice test. Yep.
Does open mean we have computers open?
Sorry?
Does open mean we have our computers open?
No, cannot have electronic devices. Other than the calculators that I bring with me to the class. So those are Dollar Tree calculators. If somebody is to walk away with one, I'm not going to be too concerned about it. I'll probably find it somewhere in the parking lot. Crappy calculator.
So we can use our own calculators?
Yep.
Cannot do binary.
Like the group our own calculators, because mine has like a base converter just on it.
That might be helpful. Might be. or might not be helpful. Yep.
Our next really assignment question the Thursday of the exam.
The next homework assignment.
The flag assignment.
Yeah,
The flag assignment.
the zero flag.
Right, but I have to finish the topics first.
Yeah,
so I have not assigned it yet.
Okay.
Yep.
Yeah, because I wanted to go look at it, I'm like,
It was showing up in the calendar as being.
Yeah, it does, because originally I was planning to assign it last Thursday, but I couldn't do it. So don't worry about the due date of the flag assignment. So this is a good way to start today's lecture, because this way we know what we need to know to get the homework assignment done. Yep. Yes.
So on question number 6, you said draw a picture of 6-bit adder. So how we put a constant there? So just box and put 0 there, called constant bit.
Yeah.
So how we gonna draw that?
Okay, there was a question about the practice exam, so let's go there first. I think it's under control unit. Okay, so the question is about which one again?
Number 6.
Number 6. Okay, so there's a question about number 6, which is down here. Draw a picture of a 6-bit adder using full adders. Clearly label the pins, terminals of each component. Using to compute 17 plus 50, label all wires to indicate whether each wire has a state of 0 or 1.
So in our diagram, we use a constant for 0. So
well, this one you just have to draw it by hand.
So how are we gonna draw that?
So I think last time I kind of illustrated like that.
Yeah.
I'm not going to draw the entire thing. So you have 2 input pins for each full adder. So you have to specify the 0s and 1s here.
How about the input one? Input carry bit. So how are we going to draw that?
Carry. Initial carry.
The initial carry is a 0.
That's it?
I will put 0 there.
Yeah.
Just a 0.
And then there will be output pins. The most important ones are the intermediate ones. Because even with a calculator that has a base conversion ability, that's not going to help with the intermediate carries. It will only help you with the final answer, but not the intermediate ones. Yep.
So 7. Which one is the 7?
Go ahead. Sorry. Go ahead. Say again. We are not going to use any tools. There will be no electronics other than the dumb calculators. Schematics will be provided to you, so it'll be printed on a piece of paper. Yes?
So which one should be 17, which one should be 50?
Well, in an addition, it doesn't matter, right?
So it doesn't matter.
It has to be consistent. You cannot say, well, sometimes I use this pin for the first number, sometimes I use the other one for the first number. That would not be good.
Is 2 plus 5 different from 5 plus 2?
I just use a
Yeah, so for
blank.
addition it doesn't matter, but for subtraction it does matter. Then you have to, you have to tell me which one is x, which one is y, and then the end result is x minus y or something like that. Yep, go ahead.
Whole period for the test?
Yeah, the entire period for the test, so we have 80 minutes for the test. Well, that's only for people who come here on time. If someone is to come here like 10 minutes late, that person will only have 70 minutes. Yep.
And once we're done, we can just leave.
When you're done, you can leave. But since I do have a lab time scheduled after the class, if you want to stay, we can talk about the solution during the lab time. And in fact, that's what I would do, is I would talk about the solution during the lab time. Even if there's no one in the lab, I'll just be talking about the whole thing, and it'll be recorded. Okay. And then everybody will be gone, right? It's like, okay. Any other questions about the exam? You will write the answers on the exam paper itself, so you don't need any Scantron. I do advise you to bring extra pieces of paper, just in case you need some extra paper for scratch work or whatever. So always bring some additional paper. Writing instruments, okay, every single test, I have someone try to borrow a pencil from another person, okay. I know how much you guys like, electronic stuff like tablets and PCs and whatnot, but occasionally you still need to have writing instruments. What's that?
What are those?
Yep. Bring a piece of charcoal with you.
Sidewalk.
Right on the table.
Yep.
Some engraving.
If you want to write on any surface, the best vandalism tool is not spray paint because that's pretty expensive. Crayon. That is nasty stuff, man.
My son does that, actually.
And it's even ingestible. It's not poisonous, but you get to tell the color the next day. It's like, I wonder which color he ate today, and you just wait a day. The next day you can find out. I will stop there. It's getting yeah. All right. So, are there any other questions about the first exam? Yep.
Is there going to be anything about the number circle on this?
The number circle will not be on.
Okay.
Because that really is going into the signed number representation, which is not included in that test. Which is a great way to kind of get into our homework assignment, because with the homework assignment, we are going to start to do things that are dependent of whether we look at numbers as signed or not. So we'll go take a look at the homework assignment, and then we'll go talk about the topics that you need to know in order to get the homework assignment done. Okay, so here's the homework assignment. Based on the original processor design, which should be fairly familiar at this point, add the following flags. We already have the carry flag, but I want you guys to add the following. One is called the Z flag or the 0 flag. One is called the sign flag, the S flag, and also the O flag, which stands for overflow. Implement these using extra gates and pins in the ALU. So they need to have extra pins because I want these to be output out of the ALU. Okay, just like the carry bit, they do not need to be stored. That's another project. Implement these using extra blah, blah, blah. Okay, there is no need to connect these to anything else in the actual processor, so they'll be dangling. Those pins will not be used elsewhere. They're not connected terminals. They're unconnected terminals. Save your design as processor.circ, circuit, and submit that file. Of course, you may want to test the ALU first to make sure that these flags work as expected for both add and subtract instructions. You can localize the testing in just the ALU, so you can set up the inputs, and then you just test the output. So you don't really need to make your own instruction to do the add or the subtract. You can just do a localized testing in this case. Note that 2 of these flags are based on the outcome of operation, regardless of whether it is addition or subtraction. And I will talk about which 2 flags. The other one does depend on the operation. You have to increase the width to the mux by 1 bit so that this operation dependent flag is switched by the mux like the carry flag. The other 2 do not need to be muxed because they're the same regardless. Okay? All right. So we'll go ahead and take a look at these flags here and find out exactly what we are going to do with these. Okay? We talked about the question. Oh, okay. Stretching. I need to give you guys flags, like, just stretching, then you can hold it up all day long, and I won't be calling you and go like, okay, what is the question? All right, so the zero flag is easy. The zero flag means the result of an operation, addition or subtraction, is just zero. Okay, so how do you know, whether the output is a zero or not? So what we'll do is we'll take a quick look. Well, I'm going to use Logisim to illustrate this because it's just it's logical to do that. All right. So we'll go ahead and just use a Logisim, and what I'll do is I will give you a general idea of what I mean by what I want to do, and then you guys kind of have to think about it, okay, how to implement it. This one has 8 data bits. I'm going to reduce it to only 4 data bits. Okay, so it has 4 data bits, and we'll go ahead and hook up some pins. Pins are under wiring, so we'll specify 2 input pins, and we'll change these to 4 bits too. So this way we can enter 4-bit numbers easily. And then we'll have 1 output pin, which is also going to be 4-bit wide, connected to the output. There we go. Oops, wrong connection. Back. Nope, that's the right. Okay, carry in this from the top and the bottom. There we go, and there we go. All right. So we have a really kind of basic setup of an adder. The half adder and the full adders are not exposed because it really does not matter in this case. If you add 0 to 0, naturally you get 0 back, right? So now the question is, how can I look at the output, which is a 4-bit output, and say, I want a flag that becomes 1 when the output is 0, but I want that flag to be 0 when the result is non-zero. Yep. You have to stick some kind of a gate. I'm not going to say which gate. I will leave it up to you guys to think about. It's not complicated. Okay? It's not complicated. But I will give you some additional idea of how to do this. And it has to do with being able to split this wire, which is a bundle of 4 wires, into 4 individual wires, because otherwise you can't really do it easily with a gate. Okay, so that part I will talk about. So we'll go ahead and attach a splitter to it, and just to make it look. All right, fine. That looks good. Okay, and it complains because this splitter currently only has 2-bit wide, so we want to change it to 4-bit wide to match the actual number of bits in this bundle. So we'll go ahead and fan it out to 4. So now we have access to each individual bit of the output. Okay. So once we can split the 4-wire bundle coming out of the adder or the subtractor into 4 individual wires, you kind of have to think about what to do so that the output out of a particular gate, or if you want to use a bunch of gates, that's fine too. The output has to be a 1 if and only if all of these wires are zeros. Okay? So the objective is to have 1 single output pin here, which is your 0 flag. So I'm going to label this as my Z flag. And you have to find out what to do in between so that the Z flag becomes a 1 if and only if the sum of this addition is a 0. Now this is not just going to be the addition, because we also have the subtraction, and it applies the same way. Then that's why in the actual ALU design, you are not going to tap the output of the adder. You can tap the output out of the mux. So whatever comes out of the mux, you hook it up to the logic thing, where the output is the Z flag. Okay, so I'll just kind of say that again. The Z flag should be a 1 if and only if the result is a 0. That's all. That's what it's supposed to do. And I'll leave it up to you guys to decide how to do it.
So if it's 0, then it should be 0. Result should be 0.
No, if it's 0,
Correct.
it's 1.
So that means, you know, if the result is non-zero, the Z flag should be a 0.
The result is not 4-bit.
Sorry?
The result is under the two number added together. The result is 0.
Well, in the actual ALU design, as I said, you're not going to just look at the output of the adder. You will tap it after the mux. You remember the mux?
Select.
Yeah. The selection thing? Yeah. All right. So are there any questions about what the Z flag is, when it should turn into a 1 and when it should turn into a 0? Yep.
Did you say the Z flag should go to the mux? That's one of the inputs, or?
No, this wire, okay,
This
this wire should be tapped into the output of the mux.
Okay.
Yep. Because we're going to do this for both addition and subtraction. It doesn't change the meaning of the 0 flag. Okay. Now you do have to be a little bit careful, because if I give you something like this, okay, so let's go into simulation mode here. 1, 1, 1, 1 here, and I'll put a 1 here. The output is still considered a 0. Okay. In other words, I really just look at the output of the operation, not counting the extra carry or borrow flag in the operation. Yep.
So the output, the 0 flag should be still
Be a 1
be a 1 in this
That
case.
is correct. All right. Yes.
Just is there any real mechanism that would allow you to, because like, you know, in C code you handle all that even bitwise like on the entire number, but down here, does it have to be individual by the bits, or is there like some other, where you can basically like you would take the result and add it, or end it with the same bit with like all one, like say if it's is there like a mechanism?
I'll let you choose how to do it. So whatever you do will take, 8 wires coming in, each wire being an individual bit, has one single output, and that output is defined as such. Your output is going to be a 1 if and only if all the input wires are zeros. But in all other cases, it should be a 0. Question?
Are we worrying about sign values?
Aha, that's a good question. We do not. Okay, we only look at all the bits coming out. We don't really differentiate the sign bit from all the other bits. Okay. So that would be the Z flag. Okay, and remember, we are tapping into the output of the mux, not before the mux. This is after the mux. Okay, that's the easy one. Another one, which is even easier, is the sign flag. So we'll go ahead and I'll put a sign flag here. The sign flag has a label of S, so it's for sign. And this is really just the most significant bit of the output of an operation. And once again, you should do the tapping after the mux, not before. Because the sign flag is going to take the sign or the most significant bit of whatever the last operation is out of the ALU. Is that okay?
I'm confused on, I think, what do you mean? What do you mean that it takes the most significant bit?
Okay, so the sign flag is really just the most significant bit of the result. Since we have a 8-bit ALU, so this is actually just bit 7. So bit 7 out of the result of a calculation, even though it is going to the registers and can be stored, but it has an extra pin known as the sign flag, so that we can do something about the sign flag with certain operations later on. Okay. Yep.
I was wondering, wouldn't I guess we're just checking for that high, the most significant bit, but
Right.
if
We're not even checking. We're just saying whatever
We're
it
saying
is
whatever it is, yeah.
the sign flag.
Because if we didn't interpret the inputs as sign bits, then isn't that also irrelevant?
The input?
Like, so if it was an addition that came in to
It doesn't matter. It is regardless of the actual operation. So whether it's an addition or subtraction, doesn't matter. We just look at the output of the operation, and then we take bit 7, whatever bit 7 is, we just say, okay, that is also known as the sign flag. So what you need to do, since you're going to splice the bundle of 8 wires into 8 individual wires, you just have to pick one of those 8 and also bring it to the sign flag. So I'm going to do the wrong thing here, possibly wrong thing here, and one of these things you just have to go to the sign flag.
Is that supposed to be 3?
I'm not going to say. I know somebody's going to ask a question, and I have the answer prepared. But one of the wires, okay? One of the wires is the correct answer. And there are 8 in your case. So you have 1 chance in 8 to get it right if you just randomly pick one.
That's not so.
But it's the most significant bit. You have to figure out what that means. What is the most significant bit? All right. So we have the sign flag and the Z flag taken care of now, more or less. The last one is the nasty one. It's called the overflow flag. Okay, so we'll go ahead and take a look at the overflow flag, which is the O flag. Okay, so I'm going to label this as the O flag. Now, this is the nasty one because we have to take a look at whether it is a subtraction or an addition first, because the way you define the overflow flag is different depending on whether it's an addition or a subtraction. Okay. So before we go any further from here, I'm going to illustrate a few examples of quote-unquote the sign of the result does not make any sense. Okay. So we'll start with addition since we do have an adder here. Okay. So I'll basically start with this one and say, okay, in this case, does the sign make any sense? If I'm using 1111 as a signed number and I add 1 to it, 0001 to it, and I end up with a 0, does that make any sense? Does the sign of the result make sense?
Yeah.
It does make sense because 1111 is representing a negative value. I don't even care how much, of a negative value. I just need to know it is a non-positive number. Okay, it's a negative number. If you add a negative number to a non-negative number and you end up with a negative number, is it okay? Possible? If I end up with a non-negative number like what we have here, is it okay? Okay, so in both cases, okay, in this case, the overflow flag should be a 0. Okay? So what I'll do is do not copy this because I'm just using this as an example. Because I know someone's going to do it. So that's why I said do not copy this. Okay. Okay, so I'm just illustrating when it should be a 1 and when it should be a 0. In this particular scenario, it should be a 0. Because if you add -1 to 1, you end up with a 0, the sign makes sense. Okay, there's no problem. Let's try something else. Let's try to add, in simulation mode, let's add 0001 to 0001. If you add a non-negative number to a non-negative number, you end up with a non-negative number. Is the sign okay? It makes sense, okay? Not a problem. Okay, cool. If you add a negative number to a negative number and you end up with a negative number, is that okay?
Yes.
Is it still okay? So the time when you have a problem with this is when you add a negative number, and when you add 2 positive numbers, you end up with something that's negative, okay? So let's see how we can do that. That's pretty easy. That is not okay. Right? Because 0111, regardless of the quantity, is a non-negative number. The other 0111, same way, it is a non-negative number. But when you look at the result, it has the most significant bit being a 1, and it's up to you to decide which one is the most significant bit. It is representing a negative value. 2 positive number having a sum of negative number, not okay. So in this case, the overflow flag should be a 1. So let's change this one. So I'm using this as a documentation method. So that means in your design it is not supposed to be hardwired to a constant 1 or a constant 2. Yep.
You'll choose to ignore my question. But to do that, we have to look at the inputs, right?
Yes, you're absolutely correct. You have to look at a part of the input, not really the whole thing, you just have to pay attention to one portion of the input.
Yeah.
Each one of the input, you have to take a look at one portion and combine that with one portion of the output to determine whether the overflow should be a 1 or a 0.
So would it be incorrect, everything you said, would it be incorrect to utilize the sign bit, or should we also be pulling from that, the output of the mux? Because I mean, because this one we can, because, okay, I don't know if I'm getting too much, but like, so we basically, we don't want, in this situation where our inputs both have their positive numbers because their sign bit's off. If our sign bit gets triggered from that output and we detected that they were unsigned, that's what I'm saying, can we utilize our own sign bit that we have in the sign
You
flag?
don't need to, because you have immediate access to the sign bit before the mux already. So I would just use the one before the mux.
Before, you mean after?
Yeah, before the mux.
The input that's coming, so that's gonna be the, because it'll be the result.
Yeah, do the splicing before it goes into the mux and pull that out. Yeah. Yep.
You can have two negative numbers and get a positive number or choose.
That would also be, one case where the overflow flag should be a 1. Okay, so I'm going to show you the other case when the overflow flag should be a 1. If we adding 2 negative numbers and end up with a non-negative number. That one is actually pretty easy too, if you kind of think about it. That would do it, right? So if you look at the 2 input into the adder, they're both negative numbers. And yet when you look at the result of the sum, it is non-negative. How did that happen? Right? So in this case, the sign of the output of the adder does not make any sense, and as a result, the overflow flag should be a 1 as well. Okay? So I have just illustrated all 4 possible cases, based on the sign of the input and the sign of the output. Yep, go ahead.
It's 0 signed according to this?
Sorry?
Is 0 signed according to this?
0, okay, 0, 0, 0, 0 as a 4-bit number is a non-negative number. And you should treat it as such. So that's why this is a problem, because we are saying that if you add a negative number to a negative number, we end up with a non-negative number. I don't even care about the magnitude, because just the sign itself does not make sense. All right? Are there any questions about the meaning of overflow in addition? But how do we do this? It's gate logic. Well, if you read the notes, it's somewhere in there. Yep, somewhere. So now it's a treasure hunt.
Yeah.
There's no X to mark the spot, but we know it's somewhere. And it's not booby trapped.
Yeah.
Okay, so if this is okay, I'm going to change the design to deal with a subtractor, and then I'll talk about the cases where when you have a subtractor, when does the overflow flag become a 0 and when does it become a 1? Okay, so let's go ahead and change this design here. Take out the adder and substitute it with a subtractor. So we have a subtractor here, stash it here. Yeah, it's going to complain because of the width is different. Okay, now we have a pretty good one. All right, so with a subtractor, it's a little bit different because when you subtract a negative number from a negative number, you end up with a non-negative number. Is that okay? Yeah, it's okay. I mean, if you subtract a negative number from a negative number, you can end up with positive or negative in that case. Okay, so that means in this case, this is a wrong indicator, so we should change this wiring. And because remember, this is really just for documentation purposes. So in this case, whatever gate logic you specify should specify a 0 for overflow. Are there any questions about why this is okay? Okay, in subtraction, if you subtract a negative number from a negative number, you end up with a non-negative number. It's fine. In fact, if you subtract a negative number from a negative number, if the sign of the input have the same, if the inputs have the same sign, the output can be anything. Okay, Because if you subtract a positive number from a positive number, the result can also be can also be positive or negative. Okay? All right. So I'm illustrating, the other case, which is flipping the input here to just, something like that. That's perfectly okay. Okay? The overflow flag should be a 0 because if I subtract, a non-negative value from a negative value and end up with a negative value, that's okay. Okay? It's not a problem. The sign makes sense.
This is bottom. We're subtracting the bottom from top.
We are subtracting the bottom from the top. That is correct. So in this case, it's actually subtracting 3 from 1 and ending up with -2. 1110 is the proper representation of -2. Yes?
How can we know it's a negative or positive number?
It's based on 2's complement, which is something that we talked about last time.
So we need to check it, all the input number, compare their.
No, you have to understand what is a signed number and which part of the number is indicating whether it's positive or negative. The number wheel we talked about last time, is one illustration of that concept. All right. So is it okay with this one too? Okay. Now on the other hand, if I specify a 1 here, so this is a non-negative number that I'm subtracting from a non-negative number, ending up with a non-negative number, that's fine too. Okay. So in this case, the overflow flag should also be a 0. So it is easier to think about when it should be a 1 instead of thinking about when it should be a 0. Okay? It should be a 1 when you subtract a negative number from a non-negative number and you end up with a negative number. That would not be good. Is that making any sense?
Oh, yeah.
Okay. So let's make that happen, right? Pretty easy too. Okay, it just happened. Because I am now subtracting a negative quantity from a non-negative quantity, and the result should be non-negative. But when you look at the sign bit of the output, it is negative. So in this case, the sign bit does not make any sense of the result, and because of that, the overflow flag should now be a 1 and not a 0. So you're going to have to specify the logic to turn the output pin O into 1 or 0 accordingly, and you have to figure out which pin to tap into from the inputs of the adder or the subtractor, and also the output of the adder or the subtractor. Okay, so your finished diagram will basically have wires coming in from the input and the output of the adder and the subtractor through your gate logic, and then have the output merged to the output pin.
And all gates are fair game?
Yep, you can use whatever gate you want to use. Yep. Okay, so what about the other case? This is one case where the sign of the result does not make any sense. The other case is when you subtract a positive number, non-negative number from a negative number. The sign should always be what? Should always be negative. But if you end up with a positive number or non-negative number, the overflow flag should also be set, or should be a 1. So I'm going to illustrate that case here. So we have a negative number here, and we are going to subtract a non-negative number here, like so, and that's it. Okay, that illustrates the concept, because right here I'm subtracting a non-negative number from a negative number, but when you look at the output, it is a non-negative number, which does not make any sense. Okay, so this is also the other case where the overflow flag should be a 1, but for subtraction. All right. Are there any questions about all the test cases that we have gone through? No questions? Okay. So you guys kind of have to think about the gate logic to take all of these into consideration. So the approximate diagram that you should be doing would be something like this. Okay. In the ALU, we have an adder. We also have a subtractor. There's the output out of each one, the input into each one. Okay. you have to basically tap into the input of the adder and the result of the adder like this. Feed all this stuff here into some kind of logic that you have to design, okay, for the adder. The subtractor, okay, so I'm going to use these things to indicate these are flyovers. So this one goes here, this one then goes here, this one and goes here, and this is another logic block, okay? The output of this one and the output of this one, they need to be combined into one single overflow flag. Okay? Because you have one overflow coming out of the adder, which uses a particular way to determine whether it should be a 0 or 1. You have another bunch coming out of the subtractor, and it has a different logic system to determine whether it should be a 0 or 1. So at some point, you have to merge those two into a single output, because we only have one single overflow flag for both addition and subtraction. Yes?
Question. Would you be able to, addition here, would you be able to go over, what would be the result of an XOR gate that takes 4 bits in?
XOR gate that takes 4 bits in. That's a good question. I do not know. That would just be, I think this is what it is. So if you have an exclusive OR gate with, okay, that looks like this, with 4 inputs, okay, let's call it A, B, C, D. The output is really just A, exclusive for B, exclusive for C, exclusive for D. That's because exclusive OR has the same properties as the other operators, is commutative and associative. So that's why you can kind of reorder these bits, you know, in the actual linear expression any way you want to. It would, yeah.
And in that case of exclusive OR, how exactly is that different from regular OR?
Exclusive OR is,
Well, I mean,
exclusive OR is the output is a 1 if and only if just one of the input is a 1.
Yeah. So it's like not X and Y.
Oh, then it's not going to be like this.
No, well, yeah, because I like I said, I don't want to say what I think. Well, I'm assuming that bit would it would only be 0 if and only if all those bits came in.
I only know how exclusive OR is defined for 2 inputs. Yeah. Let's take a look. I mean, exclusive OR is here, and well, let me show you guys another trick here. Okay, this is a trick where you can use. So instead of having multiple pins, you know, what I will do is I'm going to use a splitter here and turn the splitter into a 5-bit splitter with 5 different wires. So this is what I'll do. All right, there we go. And it will specify an input pin. That's ugly. You go here. Turn this one into a 5-bit thing, and then make it output. There we go. All right, so let's test this and find out how it's defined. Okay, if I put a 1 here, it's a 1. If I put a 1 here, it's a 0. Okay, what if I have 3 1s here? It's still a 0. So you can only have one and only one of the input being a 1, then the output is a 1. Yeah. Anytime you have more or less than 1 1, you know, then the output becomes a 0. Yeah. Yep. Which is consistent with the way we define exclusive OR, which is either blah 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 OR, right? Because you only want one of the many items to be true, but exactly just one.
No, because then you would still be.
Yeah, if all of these are on, then the output, you know, it doesn't matter, because if they're all off, the output is going to be a 0. It will only be a 1 if exactly one of the input is a 1.
Or they're all off.
Hmm?
Well, that's what I'm saying. Either one bit is
Either
on
one.
or they're all off.
No, it doesn't.
Well, no, I'm saying they'll only be.
3, 1.
No, the only time the output of exclusive OR is a 1 is when exactly one of the input pins is a 1.
Yeah.
That's the only time the output is a 1. Okay, but that's how you can test it out. You know, this is just a quick way to test out. Okay. Any other questions? Okay, if there are no questions, I'm going to move on to the next topic. No, I'm just kidding. I will go ahead and tell you where you can find this information. How do you get this homework assignment done? Okay, so let's take a look at subtraction. Okay, and when you look at subtraction, it talks about all the stuff that we have mentioned already. Okay, logic gates of a subtractor, half subtractor, full subtractor, and stuff like that. That we talked about already. But it also talks about the carry flag, which is really just a borrow flag. It talks about the zero flag. Okay, and for this one, if you read the PDF document, it is a lot better. Okay, so the negation, is basically, or the bar over bar is a is negation. Addition is basically a disjunction in this case. The next one is the sign flag, which is really just the most significant bit of the output. And this is the overflow flag. The overflow flag has two definitions depending on whether it's subtraction or addition. And here's the equation. So that's kind of the answer. Okay. So I will explain the notation. Okay, I will explain the notation once so that you guys know, how to read this stuff here. Okay. And all I need is to change this to a PDF. I have to remember how to do that. Oh, there you go. I forgot how to click on the link. Occasionally, that sort of thing happens. All right. Yep, that looks better. So when you look at this equation here, oh, this is, okay, never mind. Let me magnify this so we can see better. Okay, so multiplication is the same thing as conjunction. Addition is the same thing as disjunction. And the over bar indicates negation. It still doesn't look right to me.
Yeah.
Hmm?
No, I'm sorry.
Yeah, so in this case, the negation applies to just the D. In this case, the negation applies to, it should apply to both Y, X, and Y in this case. Okay, let me see if I can find another note that has a better description.
Is it not displaying right, or do you think you?
The notation doesn't come out right.
Okay.
Yeah, it's just a notation. Let's take a look at this one. So this one has the overflow flag.
Was that during the PDF? What if you just HTML it? Because maybe it's the PDF reader.
He was looking at it before as HTML.
It was HTML.
Yeah, this one doesn't explain that either. It just says, the overflow flag means the sign of the result makes no sense. Okay, let's try this one. Overflow. Okay, this one is for addition, so the other one is for subtraction. It shows up a little bit better, but the over bar should apply to the entire thing, overhead.
The over bar mean like the complement?
Yeah. All right. Okay, fine. Okay, so none of these is showing up, really well. So what I'll do is I'm gonna give you guys an idea of how to work on this. Okay. So what you want to do is you basically limit yourself to say, okay, I'm only dealing with addition first. Okay. When you're dealing with addition, there are certain cases you don't have to think about, because when the sign of the inputs are different, then anything can be the output. It still makes sense. Is that okay? So what you want to do is to say, okay, this is the input, this is the output, and you refer to A as the most significant bit of one of the input, B is the most significant bit of the other input, and C is the most, well, I should probably use D, is the most significant bit of the output. Okay, because it's between these 3 bits that can determine whether it's an overflow condition or not. Does that make any sense? So if you want to draw a full table, you can do that, because you can basically just say A, B, C like that, and there are 8 possible cases, right? And then the last one is just alternating.
That's your D.
Yep, that's a D. Okay, there we go. Now you have to think about the overflow flag. Okay, as I said a little bit earlier, if the sign of the inputs are different, then the output can be anything, and the overflow flag is going to be a 0. So that means for this one, it has to be a 0 here, it has to be a 0 here, has to be a 0 here, and also has to be a 0 here. Okay, it's only when the signs of the input are the same, then you have to think about, okay, is the sign of the output making any sense? Non-negative plus non-negative is non-negative. Still makes sense. Non-negative plus non-negative is negative. Does not make sense. That's a 1 here. Negative plus negative is non-negative. Does not make sense. Negative plus negative is negative. Still makes sense. So you basically look at this row here, and you look at this row here, and then you say, okay, how can I define a logical equation so that the result of the expression is 1 if A is 0, B is 0, D is 1. Or when A is 1, B is 1, and D is 0. I just spelled out the actual answer. You just have to roll back the tape and and actually write out what I said, okay? Because I was actually using the correct words. The only thing I was not using was the use of negation, okay? Because I was referring to something as a 1 and a 0. But a 0 is nothing more than a not 1, or 1 is nothing more than a not 0. So is that giving you an idea of how to do this?
Oh, yeah.
We already got answer.
That is the answer.
Answer is there.
Now she's going to use a lookup table
Yeah.
with 8 entries, you know.
Hash table?
Okay, so that's for addition. Let's talk about subtraction. Subtraction goes like this. Okay, now with subtraction we have to be careful which one is being subtracted from which one. So I'm going to use the same convention as logisim, which is the bottom number is being subtracted from. We're subtracting the bottom from the top. Okay, so now we have A, B, and D here. A, B, and D are all referring to the most significant bits of the input and the output of a subtractor. Are we still doing okay so far? The terminology? Okay. So we have the same kind of table. We have A, B, C, and if I want to be complete, I will make a table of 8 rows, 8 entries. So we have B being 0, 0, 1, 1, 0, 0, 1, 1, and then C is, D is 0, 1, 0, 1, 0, 1, 0, 1. There we go. So we have 8 rows, okay? Now with subtraction, if the sign of the 2 inputs are different, then the result can be anything and it still makes sense. Nope. Let me think about it. Yes, when the signs are the same, then the result can be anything. Okay, so that means, you know, this one, by default, the overflow flag of this one is going to be a 0 here, and then we have a 0 and a 0 here, because the sign of the inputs are the same. Is that okay? Because if the 2 inputs into a subtractor have the same sign, then the output can be anything. If the output can be anything, then they're both okay. If they're okay, the overflow flag is a 0. The overflow flag is a 1 only if the sign of the output does not make sense. Okay? So we only really have 4 cases to consider. We are subtracting a negative value from a non-negative value, ending up with a non-negative value. Is that okay?
Yes.
Yeah, that's okay. So that makes the other
Yes.
one not
Yes.
okay.
Yes.
Because we are subtracting a negative value from a non-negative value, but the output is negative. So this one is not okay. We are subtracting a negative value, I'm subtracting a non-negative value from a negative value, ending up with a non-negative value. That is not okay. And the other one is actually okay because we are subtracting a non-negative value from a negative value, ending with a negative value. That's okay. All right. So now we have a truth table for the overflow flag, but this time applied only to subtractions. Okay? And whenever you can identify and see this table only have a very few number of rows being ones, that automatically says, oh, that means I can kind of ignore all the zeros and focus on all the ones. Because my lineup thing is not right. So 1, 2, 3, 4. Okay. So I think this one, 1, 2, 3, 4. Okay, there we go. This is one row that we have to pay attention to. This is the, oops, no. This is the other row that we have to pay attention to. So what this really is saying is literally, if A is 0, and B is 1, and D is 1, then the overflow should be a 1. Or, when A is 1, B is 0, and D is 0, the overflow should also be a 1. Okay, and once again, I just really spelled out a logical equation, except, I did not use negation when it is appropriate. Okay, so you just have to kind of think about what I said, and then say, oh, so that means, just taking the negation of this and apply that to the equation. Okay? So now you have one equation or formula for overflow for subtraction. You have another one for addition, right? But you only have one overflow flag coming out of the ALU. So these two have to be combined into one output. So you have to pick a operator that has two operands, and you have to pick the right one. Well, you can either do that, or you can make the overflow flag go through the mux. Then you don't have to merge the two, because when they go through the mux, it will be selected based on the operation ending. Yep. So you can implement either way. You can either go through the mux, have the overflow flag to go through the mux, so you can save one logic gate, or you can have the logic gate and bypass the mux altogether. Is that okay? No, sort of, maybe. Okay, I'll give you one extra thing so that for those of you who are still thinking about how to implement something like this, I'll give you an example with 5 inputs, okay, and only with one case where the output is supposed to be a 1. Okay, 5 inputs. That means we have 32 cases, right? So I'll give you one example: A, B, C, D, E. Okay. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0. And most of you are thinking, oh, I want to go home, to have dinner, before tech is done with this, right? So I'm going to speed this up. 2, 0, 1, 0, 1, 1. Okay, and same time. Okay, so here's our table with 32 rows of zeros and ones. Okay, but the only one row that has an output of 1 is this one. Okay, so that means the output are zeros for basically all the rows except for this one. This is the only row that has an output of 1. How do you design a logic gate for something like this?
cisp310.
Use AND gates with inputs B, D, and E.
Oh, you could have two OR gates. You two OR gates and then you hand them out.
Well, you can do that too, but the OR gate is tricky because with the OR gate, then there are multiple ways to change the output to a 1. Okay, but by using this is basically saying, there's only one bit pattern that can turn the output into a 1, which is
Oh, because those are particular locations.
right. I'm not going to label these pins. Okay, I'll leave it up to you guys to label those pins because there's a certain correspondence between the pattern A, B, C, D, E here, and these pins here, and the bubble in front of the gate itself is a negation. Okay.
Negation.
It's a negation. The bubble is a negation. Right.
Maybe I'll do
Okay. So I'm gonna. Is that okay? I mean, is that giving you guys some clue of how to implement the gates? Now, in your case, you have 2 rows doing something like this. So you kind of have to think about how to apply this in addition to one extra thing to get it going. And if you think about what I just said when I spelled out these 2 cases, I already gave you the solution.
Here output is, because our input is 5 bits, so the output change it to 1 bit.
The output is only 1 bit. The output of this entire table on every single row is a 0, except for this one single row.
Nothing.
It's an example. Okay, that particular logic has no particular meaning other than as an illustration of how to implement that table in the form of a gate. Okay. Any other questions regarding the overflow flag? That's your homework assignment, and you have 1 week to kind of think about it, to do it. Okay. And as I said, you probably should try it out a few times. And you don't really have to implement the whole thing first into the design itself. You can just kind of do what I did here, and just pull a adder, and just kind of play with this and see if it gets the right result. Okay. Any other questions? Yep.
So we're not doing L flags or all that stuff?
No, don't do the L flag because the L flag is built on top of the sign flag and the L flag. And sign flag and the overflow flag. All right. Now, this is also a time when clicking on the wires actually is helpful because this is -8, this is 1. -8 minus 1 should be -9, but what are we getting? We're getting 7. Okay, so the result does not make any sense, right? So make use of that as well to help you understand when the sign of the result does not make sense. Yep.
Is it already set up to handle negative or positive, or do you have to do something extra to let it know that the most significant is the sign bit?
The most significant being the sign bit has to do with the 2's complement rate of inverting the number, of doing the negation on the number. So that's always the case. The adder and the subtractor are not sign sensitive. In other words, they are just doing whatever a full adder, a chain of full adder or a chain of full subtractors are supposed to do. So they're not sign sensitive at all. But it is up to your interpretation that makes it sign sensitive.
So when you hover over the pins,
the interpretation of this is 1, 0, 0, 0. If you interpret that as a signed number, it is representing -8 as a value. When you look at 0, 0, 0, 1, it is representing 1. So when you subtract 1 from -8, you should get -9. But the result is 7. The sign does not make any sense. I should end up with a negative number, but this is a positive number. Okay. So are there any questions about how to implement the overflow flag. Questions? All right. So if there are no questions about implementing the overflow flag, the next topic is what are these flags for? I mean, what do we use these flags, for in terms of comparison? Okay. So what we'll do now is I'll give you several examples to illustrate subtraction, because when you compare, it is basically subtraction. But when you look at the result of a subtraction, certain flags, have certain meanings. Okay, so we want to take a look at the result of a subtraction, and I'll basically remove the components that do not have any application here. So this is going. Okay, these are all going away. All right. So let's take a look at, in this case, we also want to look at the carry flag. So the carry flag is really just carry out of the subtractor. So this is our borrow flag, which is known as the carry flag. So we'll put C here. The carry flag is useful for a particular type of comparison. So let's take a look at the result of some comparisons, and you can tell me why, in what cases the carry flag is useful to indicate the result of comparison. Okay. Well, let's take a look at this one here. 1 0 0 0 compared to a 1 is ending with a 0 in the borrow flag. Okay. So we'll go ahead and change this a little bit. If I switch this one to a 0, then the overflow flag, the carry flag is going to be a 1. If I put a 1 here, the carry flag, the borrow flag is a 0 again. So out of this observation, what do you think the carry flag is useful for when you're comparing?
Greater than and less than?
Greater than or less than. But it only applies to a certain type of numbers. What type of numbers does it apply to? Unsigned numbers. Okay, very good. Okay, so the carry flag, which is the borrow flag out of a subtractor, is useful when you're comparing unsigned numbers. Does that make any sense? So if this first number, if the top number is greater than or equal to the bottom number in unsigned interpretation, the borrow flag is a 0. If the top number is less than the bottom number, the borrow flag is going to be a 1. That makes perfect sense, right? No? Yes? Kind of? Okay. Let's go through a few more examples. Okay. 2 versus 5. 2 is less than 5 unsigned. Okay, makes sense. What about this one? 1101 interpreted unsigned is which value? It's 13, exactly. And 2 is less than 13. It makes perfect sense. So the borrow flag all by itself is useful to indicate ordering, but only for unsigned interpretation. Okay, so unsigned interpretation, easy schneezy. Just take a look at the carry flag, and we know the result. The only thing we really know in this case is whether the top number is less than the bottom number. Okay. What about when they are the same? Which flag would indicate whether they're the same or not? The Z flag. Okay, and you have to implement the Z flag. Okay. All right. So the big challenge is not about unsigned number. It has to do with signed numbers. Okay. So let's take a look at signed numbers, and we'll go ahead and figure out what is supposed to be the result. Let's look at this picture here. If I interpret 0010 as a signed number, it's not different from the unsigned version because it is a non-negative value. So we are looking at 2 here. If I look at 1101 as a signed number, what value is it representing?
2. Negative 2.
No. It's -3. Okay, it is -3 that is representing. So 2 is greater than -3. Okay, we can make a table even. Okay, so let's go ahead and make a table here. Okay, so we'll make a table, and we're dealing with 4-bit numbers. Okay, so make sure that you remember these are all just 4-bit numbers. So in a 4-bit number, we have 2 being greater than -3. Okay, so out of this particular comparison, what is the overflow flag? The overflow flag is a 0 because you can subtract a negative number from a non-negative number, ending up with a non-negative number. That makes sense. Okay. What about the sign in this case? The sign is just the most significant bit of the output. In this case, it is the most significant bit of the output. The most significant bit is the one on the left-hand side. It's a 0. Okay, so the sign flag is a 0 in this case. Okay. Is that okay? Is everybody okay with these flags? This is overflow and that's a sign. Okay. All right. Let's take a look at another scenario. Let's take a look at 2 versus 1. Okay. 0, 0, 1, 0 is obviously just 2. 0, 0, 0, 1 is just 1. 2 is greater than 1. Okay. 2 is greater than 1. Overflow flag is a 0 because if you subtract a non-negative value from a non-negative value, the result can be either sign. Okay, so 0. What about the sign flag? It's also a 0. Okay, very good. Let's take a look at negative numbers then. This is -2. Oh, let's make a -4 here. Okay, you can click the Y to see what value it is representing, and we're going to compare that to 0, 0. Actually, that would do it. Okay, this is -5. This is -4. Okay, -4 is greater than -5. Okay. What about the flags that we are interested in? What about the overflow flag? The overflow flag is a 0 in this case. What about the sign flag? It's also a 0. Okay. So it looks like one of these flags is already enough to indicate the ordering. Okay. And then we have one last case here. Okay, we have. Okay, I think that's all the cases for greater than. Let me think about this. Yeah, that's all the case. Okay. And then we'll look at the other one. Okay, we'll look at less than. So less than is pretty much the opposite of this one. Okay. This is -6. This is -4. Okay. So -6 is less than -4. And in this case, the sign flag is a 1. And what about the overflow flag? We are subtracting a negative value from a negative value, ending with a negative value. It is still okay. All right. And we'll take a look at another one. We'll take a look at this one. Okay. This is -6. This is 4. -6. This is less than 4. And what are we getting? Well, let's take a look at the sign flag first. That's the easy one. Sign flag is a 0. What about the overflow flag?
0.
It's a 1. Because subtracting a non-negative value from a negative value, ending up with a negative value, does not make any sense.
We use -6 subtracted 4, which is -10.
-6 minus 4 is -10.
Yeah.
Then how come the output is a non-negative number?
The -10 is a negative number.
What?
That's a negative number.
-10, right?
Yeah.
-6 minus 4 is -10.
Yeah, so
But
that's
when you look at the output, it is a non-negative number. The sign makes no sense. Okay.
that's negative number. -10 is a negative number.
What?
No, look at over there. That output should be a negative number, meaning that the far left bit should be a 1, but it's not. So therefore, there's no overflow.
There is overflow in this
Yeah,
case.
that's what I'm saying. You want to look over there to make that make sense.
Do you see the result that it has a 0, 1, 1, 0?
Yeah.
If it was a negative number, it means 1, 0. It's 0.
Well, any
it'd be
negative
one
number would be
something.
one
Yeah,
something,
one something.
right?
Oh, one.
0
So
something.
that's positive number.
Yeah,
So
that's
the
why it's-
overflow is 4.
Okay, so we'll take a look at a few other cases. So we got -6, so we'll have a positive number on this side, and we'll deal with this one first, okay? So 5 is less than 7. 6 is less than 7, right? 6 is less than 7, and what are the flags? What are we getting here? We're getting a sign flag of 1. We're getting a overflow flag of 0. That's right. Because if you subtract a non-negative quantity from a non-negative quantity, you can end up with negative or positive, okay? So the overflow flag is naturally a 0 in this case. And I think those are all the possible cases. I'm just double checking to make sure I'm not missing anything, because you cannot have a positive value being less than a negative value. That does not make any sense. Okay. All right. So looking at what we have here, okay, which one flag is consistently telling us whether which side is greater? If you look at just the overflow flag, is that enough to tell me the ordering of the numbers? Nope. If you look at just the sign, is it enough to tell me which number is the ordering of the number?
No.
It's close, but not quite, right? Because this one is the one that kind of messes things up, okay? So that means the overflow flag by itself is insufficient to indicate ordering of signed numbers. The sign flag itself is also insufficient for indicating the ordering of signed values. And what are we going to do about this?
O or S.
Okay, so let me see if I'm missing one. I think I'm missing one combination, so I have to recreate that one. So
You have the one would be the only instance where that's false because the numbers are equal.
I think we got it all. Sorry, go ahead.
Well, the only other possibility is they're equal to each
Yeah,
other.
exactly. That's the only option.
Right.
So, and we'll get that from 0, from our 0 flag.
For equal to, we'll get it from 0. Basically, this is that. Yep. Now, let's take a look at equal to and see what happens, right? This is equal to. So if it's equal to, it will still fall into the greater than or equal part. So we're looking at 7 is greater than or equal to 7. What is the overflow flag?
0.
0. What about the sign flag?
0.
0 as well. Okay, so that's pretty useful. Okay, so out of this, what are we going to do about, what do I need to say when I need to indicate the first number is less than the second number?
O or S.
Yeah.
Hmm?
If O or S is 1, then it's less than.
Okay, the or does work in this case, but it doesn't work in all cases. I'm trying to think about the last case with the overflow and the sign both being a 1.
Excellent.
Okay, so let's try to think about the case where the overflow flag is a 1, the sign flag is a 1, and I need to figure out what bit pattern will create this particular scenario.
So we're still with,
Okay,
that's fine.
now it may not be possible, okay? It may not be possible. I just need to figure out whether it is possible or not, okay?
Well, we know the overflow will only be 1 if both the signs are different, right?
Right.
Depending on the input. So
Right,
first
and-
one to do that. I mean, at least if it's going to hold true for that one criteria, the numbers have to come in at a different sign, and then we want them to basically put out a 1 in the sign bit, which would mean that we're subtracting.
Okay, this is the way to think about it. We want the sign to be a 1, which means the result is negative. Now, in order for a result of negative not to make any sense, what is that forcing the other numbers to be?
Let,
Yeah, they have different signs.
different sign, opposite sign, only opposite
Look at this
sign.
table here, right? We want the output to be a 1 for overflow, and the sign of the output is a 1, so it has to be a 0 for the first number and a 1 for the second number.
Yeah.
So this has to be 0, da da da. This has to be 1, da da da. Okay? And we have.
And you want it to be so then.
And we wanted to generate the overflow, so that means we want to subtract a non-negative. We want to subtract a negative value from a non-negative value, and end up with a negative value. Okay? No, it's possible. It's absolutely possible.
Well, you don't have 8. You don't have 8 with 4 bits.
No, but that will be this condition, right?
Yeah, okay, because now you're going 0 minus negative 8, which is going to be.
Yep, that's right.
8, yeah.
So that will generate
Lecture number.
this. Well, actually, just 0 here would do the same thing too,
0, 0.
right? Because 0 is greater than or equal to negative 8. And yet, in this case, clearly the sign of the output is a 1, and the overflow is also a 1. So there is a case where the overflow is a 1, and the sign is 1 as well, and the ordering is still greater than or equal to. So now we have all four possible combinations. I knew I was missing one of them, and that's the one that I was missing. Okay, so looking at this table here, just focusing on this part here, the top 5 actually, the top 5 are all indicating greater than or equal to. The bottom 3 are all indicating less than or equal to. Okay. So that means I cannot look at one single bit, and regular OR does not work either. Because if you use regular OR, then these two will be the same as this one here. That won't work. So exclusive OR, exactly. So when you take the exclusive OR of the overflow flag, and this is exclusive OR, and the sign flag, the end result is what I call the L flag, or the less than flag, which basically indicate the top number is less than the second number, less than the bottom number, but only in signed interpretation. So as it turns out, whether it is signed or not only matters when you compare. The subtractor is still the same, the adder is still the same, it's just the flags will indicate the ordering, and that is not the same. Because unsigned number only relies on the borrow flag. That's enough already. But when you're dealing with signed numbers, you have to look at the overflow flag and the sign flag at the same time in order to determine which one is greater, whether the first is less than the second one or not. Okay. So that basically gives you a context of why we are doing the homework assignment that we are doing. Why do we care about the overflow flag? Why do we care about the sign flag? It's because we can use those to indicate ordering of signed numbers. But that just brings up the next question. Why do we care about the ordering of signed numbers, and why do we care about the ordering of unsigned numbers? How many programs that you have written for CISP 360, 400, or 430 that has no comparison in it?
Hello World?
Hello World, yeah, that's pretty much the only one, right? That is the reason. Okay, because comparison forms the most important basis for branching. Okay, should I continue the loop, go for another iteration, or should I get out of a loop? Should I go to the then branch, or should I go to the else branch? Okay. Any other questions about the flags that we have talked about? The Z flag is useful all by itself because it is telling you whether the two numbers are the same or not. Yes, go ahead.
Even in the hello world, behind the scenes, there'll still be comparison in order to get the next character.
Oh, yeah. Yep.
So.
But it's behind the scenes, we don't see it.
You don't get to see that.
Yep.
So we have 3 flags. One is 0, another is a sign, another is
overflow.
So what's this difference? What's the difference?
What's the difference?
Summarize it? Yeah, can we summarize that? I just a little bit lost.
0 is 0.
So
it
which means the result is a 0.
Okay, so if I want to find out the definition of the flags according to their meanings, this is how they should be defined. 0 flag is 1, If and only if. Does everybody understand what is if versus if and only if? Okay. So z is equal to 1 if and only if the result
Not zero.
is just 0.
It's the opposite.
And there's
The
only
zero
one
flag is saying
representation
yes.
of 0, so you don't have to think about it.
One.
Zero saying, the zero flag is asking the question, is the answer 0?
So that was false.
Mhm.
So no, it doesn't matter which order. It's saying if you add two numbers or you do any operation to two numbers, and
This-
that result is 0, set the 0
That's
flag.
the
Otherwise,
one.
leave it 0.
And then we have the carry flag or the overflow flag, which is just the carry or the borrow. That one is taken care of already, okay, so don't worry about that. We have the overflow flag. The overflow flag is a 1 if and only if the sign of the result makes no sense. I mean, that's basically what it is, right? Okay, and then the last one is the sign flag. The sign flag is a 1 if and only if the result is negative. So without using the bitwise operations or definitions, these are the actual semantics or the meanings of the flags. One to indicate whether the result is a 0 or not, one to indicate whether we have a leftover borrow or carry, one to indicate whether the sign of the result makes sense or not, and the last one indicate whether the result is negative or not. Yep.
Is that carry over borrow?
Slash, just,
Slash,
or.
okay.
Yeah, but this one is taken care of. Your homework assignment is really just focusing on the Z, O, and the S.
Okay.
Yep.
So the last one, if the result is negative, so which is the one, S, last one, S equal to 1, if the result is negative.
Yep. When interpreted signed, obviously, because unsigned numbers cannot be negative. Unsigned numbers cannot be negative.
Yeah, unsigned number always positive.
Stop.
All right. Now, but this is really important because what we are seeing here is contrary to what most people think about numbers coming from C and C++. When you think about programming in C and C++, how do you know whether a number is signed or not? You look at the type of the variable, right? Int is signed, unsigned int or just unsigned is obviously unsigned. Okay, so that's how you can basically determine, are we comparing two unsigned numbers? Are we comparing two signed numbers? We trace back to the type of the variable. In other words, signedness, or whether a number is signed or not, is associated with a value. What we are doing here is quite the opposite. A bit pattern has nothing associated with it. It really is just a whole bunch of zeros and ones. Whether it is signed or not, we use the same pattern. Whether they're signed or not, we use the same subtractor. We don't have a subtractor just for signed numbers and another one for unsigned, one for unsigned and one for signed numbers. They're basically the same thing. The only time when you have to think about, okay, is it signed or not, is when you compare. And you want to know the ordering. If you just want to know whether two numbers are the same or not, signed or not, doesn't matter, right? It seems to make sense. It only matters when you want to know, is this number greater than the other number? Now you have to be careful, because depending on whether they are signed or not, you have to pay attention to different flags out of the ALU. Okay, so this is a very different way of looking at things compared to C and C++, and this is kind of paving the way of thinking for this class, which is basically saying operations are insensitive to types. It's really just operating on the bits and saying, oh, you gave me a bunch of bits, this is the predefined operation, and I give you back a whole bunch of bits. Okay, and many operations are sign insensitive. They don't really care whether you're dealing with signed numbers or not. The only time it matters is when you compare. Yep.
So this flag 2's complement was made?
Sorry?
Was this flag 2's complement was made?
this is why 2's complement is useful, because 2's complement is used as the negation operation so that you can flip the sign of a number. And this is how we represent negative numbers. Because if I give you, okay, I give you a particular value. Okay, I can give you like 42, and I'll give you the bit representation of 42. So 42 is 32 plus 8 plus 2, so it's 0, 1, 0, 1. And then we have 0, 1 here. Nope, that doesn't look like any 0.
Yeah, because you gotta go to 16.
Okay, 1, 2, 4, 8, 16, 32.
32, yeah.
No, it doesn't look right.
Yeah, that's right.
Yeah, that's right. Yeah.
That's right.
Okay.
Right, just look, right? So
Okay. Okay.
Yeah.
Okay. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So 42 in 8 bits is represented by this particular bit pattern. What 2's complement is saying if you want to get the negative value of this particular representation, you just have to apply 2's complement to it. So if you apply 2's complement to this thing, the first thing you do is you flip all the bits from 0s to 1s and you add 1 to the end result. So that means it ends up as 1, 1, 0, 1, 0, 1, 0, 1, plus 1. And then you end up with a 0 here, a 1 here, the rest are unchanged. But the bottom line is, this is now the representation of negative 42, given that you are using an 8-bit representation. Is that okay?
is there a 2's complement circuit?
2's complement circuit is actually, you can do it with just the inversion with an adder next to it. There are many ways to implement a 2's complement operation. 2's complement is kind of interesting because it is the same thing as having 1 followed by a whole bunch of zeros, subtracting that number. It's really the same thing.
Yeah, so because I was thinking, I don't know, for that one example that we had when we were talking about, the one that you wrote in black, so isn't that going to be the case when we're basically trying to like subtract the full bit width from like
which one?
For when we're looking for a situation where the overflow is on and the sign bit is on.
You mean the first one, 0 minus negative 8?
So it's only that pattern, or do you think there's other patterns?
No, it has to be an overflow pattern, so this is the only time when it can happen. I mean, there are other things too. Anything you can, every time you do this can be a non-negative number, and you're subtracting a negative quantity from it. So
the negative.
So there are multiple ways you can do it. 2 is greater than or equal to negative 6. Will trigger exactly the same condition. Okay, but let's take a look. I mean, since we still have a little bit of time here, okay, so we'll have a 2 here. Oops, not one. This one here, and a 6 here. Negative 6. Sorry, negative 6 is bitwise not of that plus 1. Okay, so I think that's negative 6. Let me double check. Yep, there we go. See, it ends up with the same situation because we cannot represent 2 minus negative 6, which is 8. 8 is not a number that you can represent signed using only 4 bits. That is what's triggering that condition to happen.
So basically that's what the overflow means, that we're exceeding our bit width.
Right. But only for signed interpretation.
I'm just trying to see if there's like a much more specific way of like just determining, all right, this is my bit width, and then, but probably not. This is clearly smart. I'll stop.
Well, there are 2 ways to trigger the overflow flag for subtraction. This is the other way. But the other way cannot be greater than or equal to, because you always have a negative number compared to a non-negative number. So that's why it won't fit into the first half of the table. It will fit into the second half because a negative number is in fact less than non-negative number.
Yeah.
But that we have already, right? I mean, we have one case where the overflow flag is a 1, so that we kind of cover that already. All right. Any other questions? Okay. If there are no questions, I will be at the lab until 9:50. And if you want to do your homework, this one here, go ahead. If you want to study for the test and ask questions regarding, the topics for the test, I'll be there to answer those questions as well. Right. The practice test is online. It is under. Oh, I just did it, today's class too.
I need to find out how can we know it's elective or positive.
Because
It's
remember
under
I have
control
figured
unit.
out
Yeah, under control unit is just the last topic that we will be tested on, and that's why it's under control unit.
Thank you.
if it's like a 15,
Yeah.
so it's a negative 1, it's a 14.
That's all you need to take 4.
13,